Okay. So our final speaker of the morning session is James Gray, who's going to tell us about particle action, string theory, and geometry. Thank you.
So thanks very much, and thanks very much to the organizers for a lovely conference and the opportunity to speak. Also, thank you very much to one of the organizers who a few minutes ago told me in chat, and I quote, that I look like a middle-aged Data from Star Trek, which I was quite pleased about, although I don't think it's true. Okay, so we were asked to give a sort of a colloquium level overview talk. And I'm going to do that to some degree. I am going to give an overview type talk here. I'm going to be a little bit more technical than I normally would be in a colloquium, though. And the reason for that is, if you're in a colloquium in a maths department, there's undergraduates in the audience. If you're a colloquium in a physics department, there may be, for example, experimentalists who don't work with theoretical stuff at all on a day-to-day basis in the audience. And so you keep the technical level incredibly low. Here, I'm going to have a bit more technicality in, because I feel like while there's this wide range of expertise in the audience, everybody works with technical stuff on a day-to-day basis. What that means is that, I might lose some people here and there on certain technical things. What I'm hoping is if that happens, it won't detract from the overall flow. It will just be some detail that doesn't matter. So we'll see how that works. So because it's going to be an overview talk, this is not going to be a talk about any one particular paper, although I did have a paper on this subject recently. And so instead of giving the papers this is based on, I'm just going to mention a few of my collaborators that I've thought about this kind of issue with before, and the kind of issues I'm going to cover with, and hopefully I didn't miss anyone. So what am I going to talk about? Well, I'm going to talk about a certain issue to do with particle physics models that are derived from a certain type of string theory, and how those particle physics issues are related to geometrical issues in the string construction. And to get to what I want to tell you what I actually in detail want to tell you about, I need a little bit of setup first. So I'm just going to start very basic, and then we'll build up from there. And partway through, I'll tell you what it is I want to talk about. So let's start very basic indeed. We've been talking about this for a while in this conference. So we're going to start with a string theory. And as we all know from various talks that we've seen, the consistency of these string theories often demand that they have more than 3 spatial dimensions. The one I'm going to talk about here is heterotropic string theory, which is just string theory that's formulated in 9 spatial dimensions. So in particular, if I include time, which I will do from now on, that's a 10-dimensional theory. And what that means is we must hide or compactify the 6 extra dimensions if you want to have any chance of discussing particle physics, right? If you want to discuss particle physics in 4 space-time dimensions, you need to hide 6 of the dimensions of this string theory. And as has been discussed many times, the way that is done is that at each point in 4-dimensional space-time, you take there to be a compact 6-dimensional manifold of very small size, where the remaining dimensions live. And the reason that you can get away with that is any experimental probe that's been used to study nature to date, from a microscope to the Large Hadron Collider, they all have a minimum resolution, a minimum wavelength with which they probe nature. And if this space is smaller than that wavelength, you would never know it's there, at least directly. If you're working in a given framework, though, for example, in heterotropic string theory, which is unique. So if you're just working in heterotropic string theory, the 10-dimensional theory you start with is unique. And so what that means is that all the physical laws you would see in the resulting 4-dimensional universe after you've hidden the extra dimensions are determined purely by the geometry of these extra dimensions. And this is something that people have been talking about over the last couple of weeks, right? So a simple example of this is the volume of this compactification space in this heterotropic string theory will determine Newton's constant, strength of gravity. And more subtle geometric properties would determine the types of forces seen in 4 dimensions, types of particles, the interactions between those particles, and so on. And that's a lot of what I'm going to talk about today. Before we get to a little bit more detail of the construction, though, one thing I wanted to emphasize just in general terms is that you may think, well, if there's this relationship between geometry and the physics you see in 4 dimensions, why not just look at the physics we see in 4 dimensions, look at the observed physics, and then from that write down the geometry that you need to hide the extra dimensions of string theory? And the problem is that's a very hard thing to do, it turns out, practically. It's very hard to reverse engineer what geometry you need given observed physics. So what people tend to do is study a whole bunch of different geometries. If you're given a geometry, it's easier, still not easy, but it's easier to figure out what 4-dimensional physics would look like if that was the hidden dimensions of the string theory. So you study a whole bunch of geometries, and then you try and learn some general lessons about the 4D physics you get from studying that bunch of geometries. So for example, we heard Thomas talking about the Swan plan program, just as one example of this, Thomas Grimm, where he was trying to do this in a very formal way. So I'm going to do this compactification of heterotropic string theory. So I'm going to start in 10 dimensions. I'm going to hide 6 of the extra dimensions to get down to 4 dimensions. And I just want to talk about the ingredients that we're going to start with and the ingredients that will go into specifying that compactification, that hiding of the extra dimensions. So in 10 dimensions, we start with physical ingredients, which are gravity in 10 dimensions. So we're going to have a metric, Lorentzian metric. And we're also going to have an E8 gauge theory with adjoint charge fields. So if you're not a physicist, what does this mean? In particle physics theories, the interactions, the forces that you have in a theory are determined by symmetries, the so-called gauge symmetry of the theory. And if you like, this theory only has one force aside from gravity. It has an E8 symmetry, which is associated to some force. If you have a particle physics model where the symmetry determines the force, the matter fields that you would have, things like the electron in that theory, all form representations of that symmetry group. And it turns out that in this 10-dimensional theory that you start with, there's gravity, this E8 symmetry, and precisely one type of particle, one type of matter, and that's matter that lives in the 248 adjoint representation of E8. So that's what we start with. We then have to specify the mathematical ingredients for how we hide these extra dimensions, how we wrap up these extra dimensions. So I need a 6-dimensional manifold, and I'm going to take this to be a so-called Calabi-Yau threefold. Unfortunately, we had a lovely introduction to these from Watty this morning, so I won't say too much more about these. It's just some 6-dimensional manifold. We won't need much detail about them going forwards. But just to say, the reason that these are being chosen in this context is that they give rise to a symmetry that I happen to like in 4 dimensions, which is supersymmetry. And they're not the only manifold that does that, but they're the only one where you can make a lot of progress directly with techniques from algebraic geometry. And so that's what I'm going to focus on here. So we have some choice of this 6-dimensional compact manifold. That's obviously part of the setup I need if I'm going to do this picture. However, I need more information than that. We don't just have gravity, we have some matter fields and interactions living on this 6-dimensional manifold in this 10-dimensional space-time. And so we need to essentially specify boundary conditions for those other matter fields. So if we were in flat space, this would be very easy. If we're solving differential equations for degrees of freedom in flat space, we just specify boundary conditions at infinity or something, and then we would be done. But here we have this complicated topology, and so we need something more suitable for taking care of the boundary conditions on this sort of gauge matter and adjoint charge fields, this gauge symmetry and its representations. And what we're going to do is take, for example, the gauge connection to be a connection on a polystable holomorphic bundle of 0 slope. So essentially what I'm saying is we have the hidden manifold, the 6-dimensional space, and then there's this vector bundle that takes care of the global structure of all of the other degrees of freedom in the theory. Okay. These words that go around this polystable holomorphic and all this stuff, this is just ensuring that the choice of these boundary conditions, if you like, on the fields, the choice of this vector bundle respects the same symmetry that the Calabi-Yau did. So that's the ingredients we have. We have our 10D ingredients. We have the ingredients of the compactification, this vector bundle and the manifold that it's over. And then you can ask, okay, given such a setup, what would I see as physics in 4 dimensions? And for a lot of the physics you'll see, the details of the physics you will see, the answer can be determined by 2 things, group theory and bundle value cohomology or sheaf cohomology. I'm just going to take you through some of this that we'll need as we go along. So what group theory does for you in this situation is it will determine what symmetry, and remember symmetries go with forces, so essentially what forces you would see in the 4-dimensional theory. And it also determines for you what matter could possibly exist. Remember, matter fields matter in these theories appear as representations of the symmetry group. So it will tell you what representations can possibly appear in 4 dimensions. So let's see how that works. So we start with an E8 symmetry in 10 dimensions. And what that means is that the theory was invariant under this set of group of E8 transformations. But the whole setup to get down to 4 dimensions will not be invariant under that full E8 set of transformations. And the reason for that is we had to specify this gauge bundle, this vector bundle, on top of the Calabi-Yau, this thing that takes care of the boundary conditions for the matter fields. And in specifying that, we use particular choices of some of the E8 transformations. So here I'm going to take the structure group of the vector bundle to lie with an SU3. That just means I've used an SU3 subgroup of E8 as transformations to glue together the degrees of freedom living on this Calabi-Yau manifold. What that means is that the 4D theory is not going to, that's built from both this 10D starting point and this structure we're using to hide the extra dimensions, it's not going to be invariant under those SU3 transformations, because if you did one of them, you'd change some of the structure in the hidden dimensions. And so what happens is the symmetry you would see in 4 dimensions turns out to be the commutant in the symmetry you first thought of, E8, of the structure group of the vector bundle. So here, if I choose an SU3 vector bundle, which is a choice I'll make for simplicity often throughout this talk, if I choose an SU3 structure to tie together all the matter fields on the extra dimensions, the commutant in E8 of SU3 is E6, and so that's the symmetry you'll see in 4 dimensions. What matter would you see? Well, remember, in 10 dimensions, the only matter we had was in the adjoint 248-dimensional representation of E8. To see what matter you could possibly get in 4 dimensions, what representations of E6, you just ask, how does the 248-dimensional representation of E8 transform under this E6 subgroup? And if you do that, you get the adjoint representation, 27, 27 bar, and a singlet representation of E6. So that's all you can get. That's the only matter that can appear. The question you might have, though, is this is the only matter that could possibly appear, but what matter actually does? For example, how many 27 representations do you get? How many pieces of matter transforming in the 27-dimensional representation of E6? And it's the answer to that question that follows from bundle value cohomology. So remember, V is this bundle that lives over the base Calabi-Yau threefold. And if you want to work out, for example, the number of 27 matter fields that will appear in your 4-dimensional theory, it turns out that that's parameterized by the first bundle value cohomology group of the bundle over the Calabi-Yau manifold. So if you're not familiar with these cohomology groups, you can think of them as solving wave equations, Laplace's equation, on the Calabi-Yau manifold. So these are essentially one forms that are valued, that transform under the symmetry in some way. And you're solving a wave equation on the manifold, as a Laplace equation rather than a Poisson equation, to find what your massless modes will be. But for us, the important thing is that the symmetry is going to be commutant of E8 of the vector bundle structure group. And how many of these matter fields you get is determined by one of these bundle value cohomologies. And you can either think of the elements of these cohomologies in an algebraic way, they're quotients of spaces of polynomials, or you can think of them as one forms, bundle valued one forms living on the Calabi-Yau manifold. So we've got symmetry, that tells us what representation content we can have, and how much of each representation content is given to us by one of these cohomology groups. Now I did the top row here, I just did E6 as a 4D symmetry, so an SU3 structure group for my vector bundle. There are other choices. For example, I could have done SU4, SU5, which would have led to an SO10 theory or an SU5 theory in 4 dimensions respectively. So they would have different forces in that sense. The point here is that there's lots of choices, and the choices that I'm putting on this page are some of the most interesting ones because these are what are called gut groups. They're groups that can be broken down to the symmetry that's seen in the standard model of particle physics by using a mechanism that I'm not even going to mention. But these are symmetry groups that are interesting because they can be linked to particle physics. And for example, if you look at this E6 case, these 27 representations have the degrees of freedom in them they have the degrees of freedom in them of exactly one family of the standard model particles. So the standard model of particle physics has 3 families of particles. So if you have 3 of these 27s, you'd have that right particle content. Okay. The thing I want to talk about is the interactions between these particles and how it's related to geometrical features. And the interactions I want to talk about are called Eukaryo couplings. So the idea here is imagine that you have 3 particles, say A, B, and C. These would be 3 representations of the symmetry, right? Then there can be interactions between those particles. For example, particle A could decay, radioactively decay, to particle B and C. And the rate at which that happens, the strength of the interaction, is controlled by a number in the theory called a Eukaryo coupling. Now, remember, all of the physics seen in 4 dimensions in these setups is controlled by geometrical properties of the hidden dimensions. So this number that controls the interaction strength of 3 particles should be writable in terms of the geometry of the Calabi-Yau manifold, and indeed it is. And you can either write it in an integral form or in an algebraic form. So remember that each of my matter fields, each of my representations in the four-dimensional theory is associated to an element of a cohomology group, and you can think of these as one forms. So if I want an interaction between three of them, if you want a number that controls an interaction between three of these things, I could just take three of these one forms for the particles I want to interact. I could take the trace, I just mean take some gauge invariant combination of these, some combination that's a singlet under the symmetry group. There's a natural three form on the Calabi-Yau manifold, wedge it with that, and then I have a six form. I've got three one forms and a three form. So I can integrate that over the six manifold, the six hidden dimensions, and that gives you a number. Up to some factors, that number is the Eukaryo coupling. It's how strongly these particles will interact. Equivalently, I can write this down algebraically. Remember, the particles are associated with elements of cohomology groups. So what I want to do is take three copies of the cohomology group, if I want to take, for example, 3 27 fields, and I want to map them to a number, the Eukaryo coupling. And natural mappings of this type do exist. So if you're used to these things, obviously I can just basically take the tensor product and project onto the antisymmetric part. There's a natural mapping from these three to H3 of wedge free V. It's an SU3 bundle, so that's O, and H3 of O on a Calabi-Yau as a number. The point is there's some algebraic way in which you can map these three copies of these cohomology that describe the matter fields to a number, and that number is this interaction, this Eukaryo coupling. And I've done this here for E6, but similar expressions exist for the coupling in the other cases I mentioned too. Now, there's a couple of things to say here. Firstly, not all particles can interact in this way. Not all particles, particles A can decay to particles B and C. These numbers may be zero. So for example, you can never have such an interaction between two 27s of E6 and a 27 bar. And the reason is that isn't a singlet. It doesn't respect the symmetry. So if you tried to compute this integral, there's no singlet part for the trace to project to, so you get zero. And if you were doing one of these types of mappings, you'd be trying to find a mapping from H1V, that's the two 27s, and H1V dual, that's the 27 bar, to the numbers. And there's no such natural mapping that exists. And so gauge symmetry, the symmetry of the theory, forbids some of these Eukaryo couplings, but not all. For example, there's a 27 cubed coupling, it's at the top of the page. And the thing I want to emphasize is if you're working in particle physics phenomenology, so if you're not doing string theory or anything like it, you're just writing down four-dimensional particle physics models to try and match data, typically what you would say is, if a coupling is allowed by the symmetries, I should include it. If there's a coupling that you want to go away, say it's making the proton decay, and that's you've observed that's not true, and there's no symmetry forbidding that coupling and you just set it to zero anyway, in particle physics, that would normally be viewed as bad taste, right? You had no reason to set that to zero. Your model was not telling you that, you just kind of put it in by hand. So normally, if a coupling is allowed, if one of these interactions between free fields is allowed by the symmetry, you should include it. And some of them are forbidden by the symmetry and some of them aren't. This brings me to what I actually want to tell you about. So as I said, in particle physics, you would normally include all of the interactions, all of the Eukaryo couplings that are allowed by the symmetries. But if you build models of particle physics from heterotropic string compactifications of the type I described, it is in fact extremely common that these Eukaryo couplings vanish, even in cases where there's no obvious symmetry that would make them go away. And that's exciting for a couple of reasons, and hopefully some of them are clear, but I'll come to that again at the end. So the usual assumption would be if there's no symmetry, the Eukaryo coupling should be non-zero. In heterotropic string theory constructions, we seem to see the opposite. And this is due to a seemingly wide range of effects associated to structures that we saw Watty talk about earlier today. So there's constraints descending from this vibration structure he mentioned. I'll mention that again. There's constraints descending from the ambient space descriptions he was mentioning. I'm going to go over these things again in this context. And more besides. So we don't have a good overview of why this is happening yet. There seems to be this plethora of different effects that's leading to these vanishing couplings. And that's what I want to describe. But the feeling I have is that there should be some unifying cause of this underneath it all. And perhaps the interesting thing is we still don't know what that is. So let's go through and have a look at some of these effects and see how they make Eukaryo couplings vanish. So let's start with vibration. So Watty described this very nicely, so I won't give much introduction here. Our Calabi-Yau manifold, our 6 extra dimensions, some such manifolds can be described in terms of a fibration structure. The manifold can be built as a 4-dimensional base with a 2 torus tacked over that base, every point over the base. 4 plus 2 is 6, so I get a 6-dimensional manifold with a particular substructure. Now you could ask, what does this substructure have to do with Eukaryo couplings? Well, to my knowledge, the first time this was written down in the heterotic literature was by Yang and his collaborators. And the point is if you have such a substructure, it can force many of the Eukaryo couplings to vanish. So why is that? Well, think about it in the integral form. Remember, these Eukaryo couplings look like this. So I have this 3 form on the Calabi-Yau manifold, and then I have these 1 forms that correspond to my matter particles that I'm going to have interacting, and I do this integral of a 6 form. If I'm going to have a 6 form that integrates to something non-zero on a fibered manifold, 2 of the legs of the 6 form have to be on the fiber, and 4 of them have to be on the base space. If they were all on the base space, I'd get 0 because it wouldn't really be a top form. This omega has 2 legs on the base and 1 leg on the fiber. So if I write my matter fields in a basis, and I'll say a bit more about what I mean by this for the experts in a second, but if I write my matter fields in a basis where the 1 forms either have a leg on the fiber or either in the fiber or the base, then I need to have 2 matter fields from the base and 1 from the fiber, excuse me. Or this coupling will just be automatically 0. You won't have a top form to do the integral. More precisely, what I'm saying is that, so this is a special case, the general case can be done, but just to put things on one slide, take the special case where the vector bundle on the Calabi-Yau pushes down to a vector bundle on the base 4 manifold. And then you can use Leray to give a grading to the cohomology. So if you take the cohomology H1V, the vector bundle on the Calabi-Yau that's going to describe our matter fields, that can be written in terms of cohomology of high direct images on the base. It gives some PQ grading. P here in terms of what I was saying before is essentially the number of legs of the form on the base, and Q is the number of legs on the fiber. This grading is preserved under the types of products we're doing to find Eukaryo couplings, and the target space has got a grading 2, 1. So if the grading is wrong in the matter fields you're multiplying together, you get a 0 Eukaryo coupling. That's a lot of waffle. The point I'm trying to make is the mere existence of one of these fibration structures can lead to many of these Eukaryo couplings vanishing. Now, in some sense, there is a symmetry that we know about that's doing that here. It's just the diffeomorphism invariance in 6 dimensions, 10 dimensions, I guess. But nevertheless, it's very restrictive. So the question would be, and Wattie covered this morning, but I'm going to do just a little bit of it again, just to show a different way of seeing this kind of thing. The question would be is how many of the Calabi-Yaus we know about and how many of the ones that we use in building these heterotic particle physics models are fibered? If it's basically none of them, then this wouldn't be an important effect. And if it's basically all of them, then it would. So let's look at a set of Calabi-Yau manifolds. These are the CC manifolds that people like Tristan and Philip developed, and which Wattie mentioned this morning. And the idea here is as follows. Calabi-Yau manifolds are very hard to describe intrinsically because they're very complicated spaces. So one of the ways in which they're described is you just take a much simpler, bigger space, so-called ambient space, and you describe the Calabi-Yau manifold in that space as the common solution set of a series of polynomial equations. So here, my ambient space, this biggest simple space, is just going to be a product of PNs. That's what the first column does. And then I'm going to have K equations, 1 for each remaining column. I've got to stop doing that. What these columns are is sets of integers, and they're just the degree of that polynomial equation in the homogeneous coordinates of these projective spaces. Now, of course, there are constraints on these matrices. If there's some constraint on the number of equations, if your manifold is going to be 3-dimensional or 6-dimensional, if you're talking real dimensions, there's some constraint for it to be a Calabi-Yau manifold, but you can write a bunch of these things down, and Philip classified them. And in some sense, there's 7,890 of these cases of these manifolds. Now, you can ask how many of this set, as an example, is fibered. And this is what Wattie was covering this afternoon. Now, we actually gave, beyond these sort of obvious vibrations that you can see from the structure that I'm going to talk about, we actually gave a full answer to this using results by Kalar in this paper up here. But I'm just, for the ease of presentation, I'm just going to show you how, give you an idea of roughly what you have to do, how you can find some subset of these along the lines of the ones that Wattie was talking about, by using a method that I developed in the fourfold case in this paper here. So the idea is that you can take one of these matrices that describes a Calabi-Yau manifold, and you can permute the rows and columns without changing the manifold. And the reason for that is if you permute the rows, you're just changing the order you write the equations in, and that doesn't matter. And if you permute, sorry, that's permuting the columns. If you permute the rows, you're just changing the order in which you write down the Pn factors of the ambient space, and that also doesn't matter. So play around with those row and column permutations and see if you can write your manifold, your matrix, in this block diagonal form, in this block form. You have a block of Pn's, A1, another block, A2, and then a block diagonal form for the matrix where the upper left block is 0. If this top block, A1F, turns out to be a one-dimensional, a one-fold, a two-dimensional manifold, it will be a torus from the structure of some of the conditions on these matrices. And in such a case, if you have this 0, this torus is fibered over this base, with the twist of the fiber over the base being given by this matrix T. So there's just this combinatorical thing you can do to do some permutations and see if you can find, obviously you have to remove redundancies, but see if you can find some fibrations in your set of 7,890 manifolds. And you can ask how many of them are fibered. And what he was telling us about this morning, there's about 99.3% of them are fibered, basically all of them, up to a small set. As what he was saying, he and his collaborators, I've just given one of their early citations here, but as he told us about, there's many others, they looked at that in the case of these toric manifolds, where you specialize in that you only have one equation, but you generalize in that you allow more complicated ambient spaces. And in that set, they also find that over 99% of these manifolds are fibered. More than that, though, just because a manifold's fibered in one way in this case, in this way, doesn't mean it isn't fibered in many different ways. So you can ask how many different fibration structures are there in the CC dataset, and there's about 77,000 and change. And the reason that that's a little bit surprising is there's only 7,000 manifolds. So on average, one of these CC manifolds can be written in as a fibration of a T2 over some base in about 10 different ways. Coming back to Eukaryo couplings, remember, these interactions between particles are restricted. Some of them are set to 0 by the existence of these fibrations. So you can imagine that if each manifold that you're dealing with has 10 or so fibrations, there's many different possible sources of restrictions on these Eukaryo couplings, and they frequently end up all being 0. So this is very restrictive. The fact that these manifolds are multiply fibered has an implication for the particle physics models you're trying to build. Let's look at another constraint along similar lines. So we've seen from this CC case that you can describe these manifolds inside some bigger ambient space. So the actual manifold's hard to describe. So you write down some simple manifold and describe the Calabi-Yau as a solution of a set of polynomial equations inside that manifold. The existence of that structure alone can restrict these Eukaryo couplings, and it does so in a way where there is no obvious symmetry to restrict the Eukaryo couplings. So this was first, the vanishing theorems of the type I'm going to talk about were first presented in these papers by Blesniak et al. This is the Oxford group. This statement of the theorem is an incredibly small generalization of what they did. Their original theorems was just for sums of line bundles, but it generalizes directly to bundles. So this is copy and pasted from one of our recent papers. But this is Blesniak's theorem, and what it basically says, and I'm going to go into more detail on this in a minute, is take a simple case where the vector bundle, this extra structure that describes the degrees of freedom on the manifold, this vector bundle on the Calabi-Yau manifold descends from an analogous structure on the ambient space. So take the case where the vector bundle on the Calabi-Yau is the restriction of a vector bundle on an ambient space. Then again, there is a grading on the cohomology group. And this grading, basically where this cohomology describing the particles comes from as cohomologies of the ambient space vector bundle, this grading can restrict the Eukaryo coupling. So the mere presence of the ambient space, or being able to write the manifold in terms of an ambient space, even if you aren't using that particular description, can restrict these Eukaryo couplings. So roughly speaking, what's going on? This is obviously a technical slide, and I'm just doing a hypersurface to give the idea. If you have a hypersurface, or a longer sequence, if you had a more general complete intersection, you can write down a causal sequence. And here is the normal bundle to the Calabi-Yau inside the ambient space. V is the bundle on the ambient space, and Vx is the bundle on the Calabi-Yau. Then by chasing the long exact sequence in cohomology associated to this short exact sequence, you can write the cohomology that describes your matter fields in terms of ambient space cohomologies. And it either comes from a second cohomology or it comes from a first cohomology in this simple case. If it comes from a first cohomology, you call it type 1. If it comes from a second ambient space cohomology, you call it type 2. And the statement is simply that the sum of the three types of matter fields that you're looking at the interactions between has to be less than the dimension of the ambience. If it's less than the dimension of the ambient space, then the Eukaryo coupling will vanish. And that's what this theorem says. So the mere presence of the ambient space can make many of the Eukaryo couplings vanish if the bundle extends to a bundle on the full ambient space. But in fact, you can drop that later restriction. So this is something I did recently with some collaborators. Before I go on to talk about dropping this condition of the bundle coming from a bundle on the ambient space, let me just say something about these ambient spaces restricting the particle interactions more generally. So just like a given manifold may have many vibrations, the same manifold may be writable in terms of many different complete intersections in ambient spaces. In general, one of these manifolds will be writable in an infinite number of such ways, although they won't all be interesting. So for example, here are 4 CC configuration matrices. They all have different ambient spaces in the first column. They all have different defining equations that are represented by the rest of the columns of the matrix. But these 4 are all the same manifold. That can be shown by results of Philip and his collaborators, Philip Candelas and his collaborators. So potentially all of these different descriptions, and this is just the tip of the iceberg of this manifold, can give restrictions on the interactions between the particles in models that you get, models of particle physics you get by hiding the extra dimensions of string theory, heterotropic string theory on these manifolds. So how do we relax this restriction of making sure that the bundle on the Calabi-Yau comes from a bundle on the ambient space? In general, that's not going to be true. So in general, if you have some bundle on the Calabi-Yau manifold, it will not be the restriction of some bundle on the on the ambient space. And so we'd like to generalize that. That may be quite restrictive. So for example, say that for this description of the manifold, your bundle comes from an ambient space bundle. That may not be true for these 2 descriptions. And so you may lose some of the constraining power of this structure making Eukaryo couplings vanish. So this is what I did in this paper here with Magdalena Lefors, Laura Anderson, Robin Schneider, and Matt McGill. And what we did is said, generalized the vanishing theorems that Blesniak had generated to this case where the bundle on the Calabi-Yau doesn't necessarily come from a bundle on the ambient space, but rather comes from a sheaf. So the idea here is that the bundle looks much like a fibration where, or it is a fibration where the fibers are the same over every point. The sheaf, there's special loci where the fibers can differ. So it's just some more general structure on the ambient space, giving rise to the bundle on the Calabi-Yau. So here's an example of what we were able to do. So take this one ambient space. Okay, one ambient space description of a Calabi-Yau. So the ambient space is a product of 5 P1s, and I've got 2 equations defining my Calabi-Yau threefold. Then I can write 2 objects that restrict to the same bundle on this Calabi-Yau, objects on the ambient space, objects on P1 to the 5. I could write this sum of line bundles. Here, the integers just describe the first Chern class of the bundle in terms of the Kähler forms on these P1s. And of course, this is the sum of line bundles. So strictly speaking, this is an S of U1 to the 3 bundle, not an SU3 bundle, but it's not going to matter. So I'm just going to gloss over it. This restricts to some bundle on the Calabi-Yau, and so does this sheaf. This sheaf on the Calabi-Yau restricts to the same bundle on this sheaf on the ambient space, restricts to the same bundle on the Calabi-Yau as this bundle on the ambient space. How have I generated this sheaf? I've just multiplied the first line bundle here by what's called an ideal sheaf. That's just, it's some spiky object. If you're not familiar with this stuff, if you are, it's defined by the usual short exact sequence, and the locus, it's a curve in the original space that the ideal sheaf is associated to, is given here. So the idea is this goes sheafy over, it goes funny over some curve, and that curve misses the Calabi-Yau, and that's why these 2 things restrict to the same object. What's the point of doing that? Well, you find that you can generalize the theorem. Have we got about 5 minutes? Yeah. You can generalize the theorem that Blesniak et al. Had to something relatively general, where you just need some resolution of your vector bundle on the Calabi-Yau in terms of sheaves, and then some constraints on the cohomologies in the sequence to get vanishing Eukaryo couplings. And that can be applied to this case. So that can be applied to the case where you have a sheaf on the ambient space, not just a bundle. And what you find when you do that, unsurprisingly, is that different lifts to the ambient space of the same vector bundle give rise to different constraints on the Eukaryo couplings. So, for example, in the case I just showed you, if you just try and apply this theorem to this sheaf, it leads to no constraints on the Eukaryo couplings whatsoever. But this vector bundle tells you, when you apply these theorems, tells you that all of the Eukaryo couplings are vanishing. And so in this model, all of the Eukaryo couplings vanish, but you get different constraints from different lifts of the bundle on the Calabi-Yau to the ambient space. In general, there will be many such lifts, an infinite number. And so you end up with this situation where you've got vast numbers of different descriptions of a Calabi-Yau in terms of different ambient spaces. For each ambient space, you can raise the vector bundle on the Calabi-Yau to some object on the ambient space, a sheaf in general, in many different ways. And all of that different structure, all of it can constrain the Eukaryo couplings, can set some of them to 0. And this is why we get this weird feature that in these heterotic models, even though there's no symmetry seemingly restricting the Eukaryo couplings, often when you actually calculate them, they vanish. Now, one thing I should say is that in general, for this kind of effect, there's no known symmetry that would be setting these Eukaryo couplings to 0. In this particular example, there is, and that's because we made it that way. The reason that we chose an example where there was a symmetry that we knew was forbidding the Eukaryo couplings is we wanted to check that the theorem was working correctly. So it's very easy to come up with cases where there is no symmetry, but in this one, we can check that the answer is correct. All the couplings do indeed vanish by using a known symmetry. There are other things I haven't discussed. So there are structures that I explored with Andre Lucas, Bert Overath, and Lara Anderson to do with the stability, the polystability of the vector bundles that cause constraints on Eukaryo couplings because of the holomorphy of the superpotential and so on and so forth. There's many other constraints, but I hope I've given you an idea that there's this plethora of geometrical structure in one of these string compactifications that lead to something interesting for particle physics. That's that the interactions between three matter fields in the resulting particle physics theories are often vanishing, even in the absence of any symmetry that tells you that they should, because of all of this structure. One question that you might have is, all of these different effects I've been talking about, do they actually all give the same results? So the vibration constraints give the same results as the ambient space? And the answer is no, and you can just see that by playing with examples, which we do in the paper. And so this kind of leads to what for me is a very interesting set of just two possibilities. There's just two possibilities for what can be going on here. The first possibility is actually in these 4D theories that come from heterotic string compactifications, a subject that's been studied for 40 years, that there is a symmetry that we don't know about that is forbidding these Eukaryo couplings. That would be amazing, because symmetry is the bread and butter of how we control these compactifications. And if there's one we're missing, it's absolutely crucial for us to find it. The other possibility is that these vanishings are genuinely quasi-topological in nature. There is no symmetry that's making these interactions between particles go to 0. And that's fascinating too. Because remember, in phenomenology, if people were just building normal particle physics models, if there was no symmetry forbidding a coupling, they would just say, well, I have to include that coupling, and if it makes the proton decay, well, my model's bad. If you took as motivation heterotic string theory, then you might have justification for this particular type of superpotential high energy Eukaryo coupling to say, actually, I'm going to assume that that coupling is 0, even though there's no symmetry, because maybe one of these quasi-topological effects forbids it. So either possibility is exciting. At the moment, I don't think we know which it is. I have my suspicions, but we don't know which it is. And we just have this wider range of effects that we can look at in different contexts that give these vanishings. So I'll stop there. Thanks very much. And are there any questions?
I'll thank James. Very nice talk. And questions.
I have a question, James.
Hey, George.
So these two possibilities, right? If I were to think from the effective field theory point of view, right? I guess this is a prediction of UV physics, right?
For particular types of UV physics, I agree.
Particular type of UV physics for my effective field theory.
Yeah.
So, okay, let's envision, like, for example, there is a new symmetry. What would we actually have in mind? I mean, are we talking about some textures on the Eukaryo couplings?
Oh, I see what you mean. Very good, George. Yeah, excellent question. So here's some details that I've been furiously sweeping under the rug because I didn't have time to talk about it, right? So what we're talking about here is superpotential, tree-level superpotential Eukaryo couplings at high scale. Okay. So first of all, there'll be higher energy corrections to this that will be suppressed by mass scales of the compactification scale.
Yeah, of course.
Second of all, I'm saying stuff George knows here, but just to be complete in the answer.
Yeah.
Second of all, there'll be running of this stuff down. And as you say, what that will generally do is lead to textures.
Yeah.
There can be cases where it can completely change the scale of what's going on. So say, for example, that you have, which is not unusual, that you have a case where literally all of the Eukaryo's go away. These superpotential Eukaryo's go away.
Yeah.
Then the compactification scale doesn't appear naturally in the Eukaryo's in that way anymore. And so you really do change the scale of what's going on. They come from, say, non-perturbative effects or something lower. And so these can have these subtle effects, but you're right, it's not as simple once you go to the phenomenology as something being zero or not, but there's still an effect there.
Well, okay, so that I mean, with symmetries, I was thinking of textures, but it's very hard for me to think about the vanishings that are due to this sort of quasi-topological nature from the effective field theory point of view. I don't know what I think about there. Are we
Neither do I, and that's why no one's written anything down. One thing that's particularly hard is their inequalities. It's very easy if it's an equality because you just say, okay, then it's not the gauge invariant, it's not invariant or something, but the inequalities make it hard.
It'd be nice to come up with some type of toy model for this. I mean, just given this general message that you're uncovering, well, I mean, in this particular case, I'm not saying that it's totally general, but in this specific case, I mean, it is, it seems like something new for effective field theory, especially when it comes to this quasi-topological nature.
Yeah, I guess you're plumping for case 2 here.
Sorry?
Which is fair enough. You're plumping for case 2. Yeah, I mean, that's fair enough. That would be interesting.
Okay. All right. Okay. Thank you. It was a nice talk. Thanks a lot.
George. Nice.
Thank you. Yang next, and then Carlo.
Thanks. Thank you very much for a nice talk, James.
Thank you.
And the question is similar to the previous one, actually. So in this case, where the Eukaryo's are vanishing because of these quasi-topological arguments, this argument still survives in perturbation theory. So they forbid the emergence from loops or non-perturbative.
Very good. No,
because you want to have a hierarchy, a pattern of Eukaryo couplings. I mean, you don't want the 3 families all belong to have the same strength. So
very, very, very good. Yes. So first of all, the answer is no. They do not survive that. What will happen is you will have terms that are suppressed beyond these. So if these terms were present, they would be numbers. Then there'll be terms that are suppressed by things that look like small vev over compactification scale. You will also have non-perturbative contributions to these that are there as well. The point is that the size of the things that will be present are, in any controlled regime, are automatically smaller than the thing that went to 0. So it is more subtle, it's more, as I was saying to George, I swept a load of stuff under the rug, you're right to call me on it. There's also going to be the running, but there is still a noticeable effect. So for example, just to give you one case in point of this, if you look at the scales in these models and so on and so forth, if the top Eukaryo vanishes, even with all the corrections, you're going to have a real trouble getting the top mass.
Yeah, but on the other hand, if the top Eukaryo is different than 0, but the others are vanishing, and you can generate perturbative, non-perturbative, this will, you like.
Right. You're talking the dream, really, right? That would be lovely. Yeah.
And so the second question, sorry if I can, related also to the comment that what he made at the end of this talk about the status of the standard model, because I understand that getting the spectrum is, I mean, you have plenty of compactification which give you just the spectrum, but the devil hides in the details, and the Eukaryo's and the hierarchy, what is the status?
Very good. So as you say, there's thousands of models where you get the right spectrum. That's not hard to do. Well, it's hard to do, but it's been done, I guess is the right, well, fair way to put it, right? Then Yukawas, well, I'm basically telling you what we know. So that's where things are there. Then after that, things that you would want to know. Well, first of all, you'd probably want to know the matter field Kähler potential.
Sorry?
The Kähler potential for the matter
Sure.
field. You probably want to know that first. Still very little known on that. That's what's driving a lot of the numeric work on Calabi-Yar metrics. There's some work by Pauti, Lucas, and other people that I forget the name of, I'm sorry, doing it in certain cases, but the matter field Kähler potential is one of the pieces that's still missing there. After that, after you've done those things, the obvious thing that's missing is supersymmetry breaking, sort of tying into what you were talking about. And there, because we don't even know stable vacuum here yet, right? So,
No.
yeah. So I would say that's where we are. We need Kähler potential, we need supersymmetry breaking, and we need to understand this.
Okay, thanks.
Thanks.
It wasn't great. Did Yang have a question for you next? No, you didn't. Okay, then Tristan.
Hi, James. Very good talk. Thank you for this colloquial level overview. I just wanted to comment actually on your, what appears to be a dichotomy, but I think it's not. The two are really profoundly related in string theory. And this is perhaps a novel lesson from string theory. Recall that even the choices of symmetries that you have in string theory actually stem from some sort of topology, because we do have EA cross EA because it's a self-dual lattice, which in turn comes because of modular invariance, which has to do with the topology of the world sheet and so on. So the two things that you note here as different are not really easily
I would disagree with that.
separable.
I would disagree with that. So what you're saying is, of course, true, absolutely, and it's a fine point. I would say you're actually plumping for version 1 there, because in all the cases you mentioned, there's topology, but there is also a symmetry, right? I mean, you actually have the symmetry there. It's just linked to this topology in exactly the way you said, and it's, of course, an excellent thing to point out. The trouble here is I don't know what the symmetry is. So I would say you're plumping for point 1. If there's that topology there, there must be a symmetry somewhere, which is a very reasonable point of view, but I point out it's the opposite to the one that George was plumping for. So,
I'm trying to count that the two are profoundly related. They're interlinked or so, you know, to quote Dennis Sharma via Philip Candelas, it is fascinating to learn that the number of neutrinos is counted by the Euler number of Calabi-Yar manifold. So, you know, is that topology or is that symmetry, or it may end up turning out into semantics. We may end up learning through string theory that there is a sort of wishy-washy symmetropology or something, and sometimes shows up as symmetry, sometimes as topology.
yeah, it's a fine point. And if that turns out to be true, then that's what I mean by point 1.
Cool.
Yeah, fine set of comments. Thank you.